Well, hello and good evening, pre-calculus. So this is the completion of the notes that we would have covered today in class, continuing our work on solving trigonometric equations. I'm sorry I'm not going to be able to be there today. I have a sick kid here at home that I'm going to be snuggling instead, so know that I will be missing you dearly, and I look forward to catching up with you guys all on Friday. So diving into the rest of the examples, you'll be able to then work on the worksheet passed out by your sub and be able to get started on that, bringing in your questions for Friday. I have a couple of examples I want to work through, you guys. You'll notice that these are the notes on Kami. You'll be able to see this for all three of the periods, 2nd, 4th, and 6th. So let's dive in. So first, we're looking at solving 1 plus the cosecant of theta equal to -1. Just like we've talked about before, you're still applying all of your regular steps for solving. So here you have that 1 plus the cosecant, so you'll be able to subtract the 1 on both sides. And when you subtract the 1 on both sides, you get your cosecant here of theta equal to -2. And now this is what you're checking and looking for on the unit circle. If we take this one more step, we'll be able to see by applying our cosecant inverse that our theta is equal to the cosecant inverse CSC with the -1 of -2. But that right there is the exact same thing as the reciprocal of cosecant, and the reciprocal of cosecant is sine. And so this is the exact same thing as saying the sine inverse, but instead of having -2, you're taking it of the -1/2. So on your unit circle, answering the cosecant of -2 is the same thing as answering for the sine of -1/2, and you'll see on the unit circle that we have the sine value of -1/2 and in two places, both in the 3rd quadrant and in the 4th quadrant. And so we have our value of theta equal to that 7 pi over 6, as well as that 11 pi over 6. But because we are not restricted to any set range, any set interval for our radians, we are adding on that 2 pi times our counting integer. So 2 pi times k, and theta is also equal to that 11 pi over 6 plus 2 pi times that k value. Now, one more thing that I want to add. K is just a variable, like every other variable in the world. And so often, if you do not see k, the other most common variable you'll see, erasing those k's there for emphasis, is the number represented by the letter n. So both of those are just as appropriate, an n value or a k value. So that completes that first example. Next, let's take a look at this more complicated example with tangent. Like we said before, we're still applying all of our numeric sense and solving strategies. So you see a fraction, you can undo the fraction with multiplication. Here, we see that the tangent of theta is being added by a -4. And so when we think about solving that -4, the first thing I would want to take care of is trying to understand the problem more completely by splitting up that fraction. So I'm going to choose to rewrite the -12 over 3 separate from the square root of 3 over 3. What other things do I notice that's informing my decision? I know that the square root of 3 over 3 is a common value seen in the unit circle. That's the reciprocal of 1, it's not the reciprocal, excuse me, that's the simplified radical of 1 over the square root of 3. So I'd want to get that isolated because I know that's going to be valuable as we go and solve the problem. Those are patterns that we're able to recognize and rely on. And so on the other side, we have that -4 plus that tangent of theta. And here we'd undo that subtraction with addition. So we're going to add by 4 on both sides. And here, you guys can probably already guess what's going to happen when you have negative 12 divided by 3. That gives you a negative 4. Then you have that plus 4 we just added on to both sides, plus that square root of 3 over 3 equal to the tangent of theta. And who'd have thunk it, the two negative 4's are going to cancel out, just leaving us with, zoom, just leaving us with that square root of 3 over 3 equal to the tangent of theta. Now, like we've talked about before, that square root of 3 over 3 comes from simplifying the radical, which is 1 over that square root of 3. And we all know the definition of tangent is sine of theta divided by cosine of theta. So the values we are looking for, the radians we're looking for on our unit circle, is where the sine of theta is a value of 1/2, because it has that 1 that corresponds, and the cosine of theta has that value of the square root of 3. So on the unit circle, where do we see the sine having the value of 1 and the cosine having the value of square root of 3? We see that at pi over 6 at 30 degrees. So our value of theta is equal to that pi over 6. And then you have that repetition, but here, instead of it being 2 pi, the period of tangent is pi. So we're going to add pi times n. Now, what's the other value that's a positive 1 over square root of 3? If you look at the unit circle, you see that the sine has a value of 1 at 7 pi over 6, and the cosine value has the value of negative root 3 in the numerator at 7 pi over 6. So we can continue to write the other angle as 7 pi over 6 plus pi times n. Now we would be done here, except there is a really valuable observation that comes with having comfort with adding and subtracting fractions. When you observe this problem and you look at the fact that we are adding by pi times n, you should notice that pi over 6 plus 1 whole pi gives you 7 pi over 6. Which means we actually don't need to represent our two separate angles as two separate answers. What we have written down here is the same answer written two different ways. So in order to be concise in our answer, in order to communicate it as efficiently as possible, we only need to write this. We could ignore this completely because that's already included with our pi over 6 plus our pi times n. Going around the unit circle, which I should repeat, is only half of the unit circle from pi over 6 to 7 pi over 6, back to pi over 6, back to 7 pi over 6, over and over and over again. And that's because the period is pi and not 2 pi. Now, let me show you two more examples, and these are going to be more complicated. They're not going to be more complicated in terms of our trigonometry. We're still just looking where on the unit circle do our tangent, sines, and cosine values occur. They're going to be more complicated because of the other possible misconceptions and difficulties working with fractions, working with square roots, and working with positives and negatives. And so I'm going to zoom here on my paper. Don't get dizzy. Here we go. So here we're solving a more complex problem. And so let's use those same strategies, use those same abilities of simplifying fractions in order to get our theta by itself. First, like I talked about before, I find it to be an effective strategy to simplify our fractions and split that up so we can isolate that square root of 3, which we know is a really important value on the unit circle. So separating our fractions here, we have the 2 minus 3 divided by 5 secant of theta equal to 10 over 5 plus the 2 square root of 3 over 5. So I notice that 10 divided by 5 is 2. Makes that pretty easy, right? So 2 minus 3 divided by 5 secant of theta is equal to 2 plus 2 square root of 3 divided by 5. And I'm sure many of you have already anticipated what's going to happen here. Subtract by the 2, subtract by the 2, and golly gee williker Batman, those are going to cancel out. So now what do we have? We have our negative 3/5, because that negative still hangs out, secant of theta equal to 2 square root of 3 over 5. And now in order to solve this problem, we are solving with fractions. And if you're really comfortable with fractions, you can probably do this in one step. I'm going to take care of this, talking about it in 2 steps to help add that clarity. So here we are dividing by 5. So to solve dividing by 5, we're going to multiply by 5 on both sides. What's nice is that the 5s are going to cancel out on the side with the secant, and the 5s are going to cancel out on the side with the square root. 5 divided by 5 eliminates. But we also have that square root of 3. Well, looking at the 3 next to the secant, if we want to get secant by itself, then if we are multiplying 3 by our secant, we undo multiplication with division, so we will divide by negative 3 on both sides, which puts it on the bottom of the fraction. And so simplifying this out, after the 3's cancel out on the side with the secant, we have the secant of theta equal to 2 square root of 3 divided by 3. And a positive 2 root 3 divided by a negative 3 makes that a negative number. So what do we do from here? When we're looking at this value, what's actually happening? Well, let's rewrite this in a way that makes more sense, a way that we can understand what we're looking at more clearly. And so that, once again, uses this square, oh here, what color should I pick? I'm going to pick teal. Uses this square root of 3 divided by 3. We know the square root of 3 divided by 3 is the simplified version of the root 3 in the denominator. So this is the same thing as writing the secant of theta equal to negative 2 divided by the square root of 3. Now, if that doesn't click into place yet, let's examine our understanding of what secant is to help complete this picture. Because secant is a reciprocal of cosine. So this is the same thing as saying that we have the cosine of theta equal to that negative 2 over square root of 3 flipped, the reciprocal of that fraction. So what we're looking for is the negative square root of 3 divided by 2. Now, that is only obvious, and that only makes sense if you're comfortable with simplifying the radicals in the denominator, and if you're comfortable with your reciprocals, flipping your fractions, because that's what enables us to see on our unit circle that the cosine of negative 3 over 2 happens at that 5 pi over 6 in the second quadrant, and at that 7 pi over 6 in the third quadrant, where we have those negative x values. And so I'm going to go ahead and zoom out just a smidge so I can give myself a wee bit more space. And so rewriting this in a couple of different ways to build up your comfort in the notation that we are using, right? The secant of theta equal to negative 2 over square root of 3 is the same thing as saying theta is equal to the secant inverse of that fraction. But I'm going to choose to write this simplified fraction. I'm going to choose to write that negative 2 square root of 3 divided by 3. Because that is that simplified way of writing negative 2 divided by the square root of 3. That's simplifying and rationalizing the radical in the denominator. And like we were practicing, that should feel comfortable saying that that's the same thing as cosine inverse of that flipped fraction, the cosine inverse of the negative square root of 3 divided by 2. And so, regardless of which of those use, which I want to emphasize, this right here is what you're looking at and using if you happen to be using a TI-84 or another Texas Instruments, right? Texas Instruments does not have a lot of accessibility for using secant, cosecant, and cotangent. So our reciprocals and feeling comfortable with looking at our inverses with reciprocals is necessary depending on the tool we're using. Either way, our theta is the second and the third quadrant. So our theta is that 5 pi divided by 6 plus the period of cosine, which is 2 pi times n, and that third quadrant, the 7 pi over 6 plus the 2 pi over n. And here we're done. This is the final answer we're looking for, and we can feel confident in that because, unlike the tangent example we just looked at, going around the unit circle, the whole unit circle by 2 pi, takes us back to 5 pi over 6, and it does not actually end up including the 7 pi over 6 values. So we need both of those separate equations to actually fully represent all of the possible values of theta. Now, last example. Ladies and gentlemen, we have cosine on both sides of the equal sign. How exciting is that? The good news is, in solving this, is still using the tools and skills you're already familiar with. When you combine like terms, whether they're x's or y's, or in this case, cosine of thetas, you're still applying those same patterns of combining like terms. So let's do that here. Let's combine some like terms. We know that we can combine our values of 1. I'm going to choose to go ahead and add 1 to both sides. And when we add y1 on both sides, the 1s are going to eliminate. Boom, boom. So what we're left with is just that negative cosine of theta equal to 2 square root of 3 plus cosine of theta. Now I need to get my cosines onto one side of the equal sign. I want to get my theta by itself on one side of the equal sign. So I'm going to subtract by the cosine of theta on both sides. And over here on the right, where we have our 2 square root of 3, those cosines are going to cancel out because addition undoes subtraction. And now my equation is that negative cosine of theta minus cosine of theta, leaving me negative 2 cosines of theta, just like as if they were variables like x or y. And that's equal to 2 square root of 3. So what do we do from here? Well, we identify our operations. What's happening between negative 2 and cosine is multiplication. What undoes multiplication is division. So we're going to divide by negative 2 on both sides, meaning that our value of our cosine of theta, needs to be equal to negative square root of 3. Now, you should be looking at that and going, wait, where on the unit circle does the cosine of theta equal to negative 3? We've talked about matching that with tangent and looking at the values where the cosine's negative 3 in the second and in the third quadrants. But unlike with tangent, there is no division of sine or cosine. So the 2's don't cancel out here, right? This is asking the same question of where is our theta equal to the cosine inverse of the square root of 3? And you may have already reached this conclusion, but ladies and gentlemen, the square root of 3 is roughly right around 1.7. And if you look at the unit circle, the cosine never is larger than 1. Our x values on our unit circle go up to 1 and go down to -1. If you ever have a value that's larger than 1, there is no radian that gives you that answer. So theta cannot exist. There is no solution. That can give us a value larger than 1 when we take the inverse cosine or the inverse sine. And so, even though we did all that fancy math and combined our cosines and we're feeling really proud of ourselves, unfortunately, because of that square root of 3, because 1.7 is larger than 1, there is no solution. So, ladies and gentlemen, at this point, what you can feel confident in doing is going to that worksheet, working through those examples, working through those problems. You're going to see that they're going to be rigorous and slightly complicated because of those fractions and those square roots and those reciprocals and that whole skill that's new of applying our inverse trig operations to solve with trigonometry really comes down to comparing it to that unit circle and looking for those corresponding radian values. So, ladies and gentlemen, good luck with your practice and good luck with your work. I look forward to catching up with you guys tomorrow.